We have looked at the intuition behind PCA and we have worked out a numerical example. Now let us look at the mathematics behind PCA. You are expected to know the mathematical foundations in eigenvectors and eigenvalues. The basic steps in PCA are: we get the training data, we normalize the data, we perform translation on the data, we perform rotation on the data. At the end of it, we get coordinate axis called the principal components, and then for the new coordinate axis, we get the new data points. Some of the notations that we are going to use are: the data points after normalization, we call it as the set X. Each data point in X is referred as xk, and the mean of X is given by X bar. After applying PCA, the data points that we get is referred to as Y, and every single data point in Y is referred to as Yk. As the first step after normalization, we need to perform translation. We change the origin of the new axis. To change the origin of the new axis, we take the mean of the data points of the normalized data. Xk refers to the data points in the normalized data set and X bar is the mean. The new Yk is such that we first perform a translation using the formula Xk minus X bar. To perform a linear transformation of the data set, we first perform a translation and then we perform a rotation given by the rotation matrix E. I want my E to reflect the coordinate axis, and the coordinate axis should be in such a way that the first axis is the direction in which the data points have the maximum variance, and the second coordinate axis gives the direction in which the variance is second maximum, and so on. So I need to take the variance of Y. Remember, Y is the new set of data points after applying translation and rotation. The variance of Y is given by 1 by n minus 1 into sigma over k from 1 to n yk minus y bar the whole square, which I have written as yk minus y bar into yk minus y bar. I can write it as a dot product of two vectors yk dot yk. What happened to the y bar? The mean is 0 because we have already taken the mean subtracted data, and so the mean of the new set of data points will be 0. We can write it as matrix multiplication given by yk transpose into yk. Yk has already been written as xk minus x bar into E. Substituting that in the equation, we get xk minus x bar into E the whole transpose into xk minus x bar into E. I take the transpose inside. So the first part becomes E transpose into xk minus x bar the whole transpose. I take those terms which are independent of sigma outside. So I can write it as E transpose into 1 by n minus 1 into sigma over xk minus x bar transpose dot xk minus x bar into E. I can rewrite this as E transpose into the covariance of X into E, which is nothing but E transpose dot C dot E, where C refers to the covariance of X. The objective was to maximize variance, so we just concluded that we need to maximize E transpose into C into E. Since E is a rotation matrix, it should follow the constraint E into E transpose is equal to I. Now, the entire problem statement becomes maximize E transpose into C into E subject to the constraint E into E transpose is equal to I. It has become a constraint optimization problem. And this constraint optimization problem can be solved using Lagrange optimization. Lagrange optimization can be applied to problem statements which can be stated as optimize f of x subject to the constraint g of x is equal to 0. Here, in the place of optimize, we had maximize, and in the place of f of x, we had E transpose into C into E, and in the place of g of x is equal to 0, we had E into E transpose is equal to I, or E into E transpose minus I is equal to 0. By Lagrange method, if I have an objective function and a constraint, I can write the Lagrange equation as L of x comma lambda is equal to f of x, the objective function, plus lambda, the Lagrange multiplier, into constraint, which is b minus g of x. This is maximum at d L of x comma lambda by dx is equal to 0. Rewriting the Lagrange method for our problem, we get L of E comma lambda is equal to E transpose into C into E plus lambda into E transpose into E minus I, and this is maximum at dL of E comma lambda by dE is equal to 0. To find the rotation matrix E using Lagrange optimization, we equate dL of E comma lambda by dE to 0. That is, in the place of L of E comma lambda, we substitute E transpose into CE minus lambda into E transpose E minus I. Differentiation of f of E into g of E by dE is equal to f of E into differentiation of g of E plus g of E into differentiation of f of E. Assume f of E is E transpose and g of E is CE. Applying the formula, we get E transpose CE. When we differentiate, we get E transpose into C plus CE. Differentiating E transpose into E, we get it as twice lambda E. This can be further written as twice CE minus twice lambda into E is equal to 0. Rearranging, this can be written as CE is equal to lambda E. The eigenvectors and the eigenvalues we have learnt in linear algebra. So now, we already know that C is the covariance matrix. Since we have CE is equal to lambda E, lambda is the eigenvalues of C and E are the eigenvectors of C. So I have concluded that E, the rotation matrix, is nothing but the eigenvectors of the covariance matrix of X. As a last note, let us see how to write old data points in terms of the new data points. The new data point is given by yk is equal to xk minus x bar into E. Let's take the E inside, so it becomes xk into E minus x bar into E. Rearranging, we get xk into E is equal to yk plus x bar into E. And what we are trying to find is xk when we have the values of yk and E. When we take the transpose on both the sides, we get xk into E the whole transpose is equal to yk plus x bar into E the whole transpose. When we apply the transpose inside, we already know that AB the whole transpose is equal to B transpose into A transpose. So, E transpose into X transpose is equal to YK transpose plus E transpose into X bar. Multiplying by E on both the sides, to get the value of XK, we get E into E transpose into XK transpose is equal to E into YK transpose plus E into E transpose into X bar. But E into E transpose is equal to I. So XK transpose is equal to E into YK transpose plus X bar. Taking transpose on both the sides, again we get XK is equal to YK into E transpose plus X bar. Concluding, the normalized data can be retrieved by new data points into the transpose of the eigenvectors plus mean of the normalized data. If you remember, this is what we have already done in the worked out examples under the part 3 video on PCA.